Today I'm very happy to invite Liang Huang from University of Pennsylvania. Liang is a very young senior graduate student. He has been doing very good work in parsing and recently used parsing for machine translation.
Thanks, Decoder. So thanks everybody for coming here. And the talk today will be on forest-based search algorithms for NLP and parsing and translation in particular. So before I talk about any technical details, I want to first convince you guys that search, even for us human beings, is not a trivial problem. Because if we are given a sentence, we kind of search over the possible interpretations to get the most probable answer, but that's not an easy task. For example, this is a real story. My advisor, Aaron Joshi, was once asked to teach high school students what's NLP and what's like parsing. So that's apparently a very challenging task for those little kids in their early teens, like what's context-free grammar, what's bottom parsing. But Aaron found a better way to do that, basically just speak a sentence and let them draw whatever they have in their mind. So for I saw her duck, there's one kid who got this. I saw her duck. So this is apparently a word sense disambiguation problem for the verb saw. And for the next sentence, I eat sushi with tuna. That girl got this, basically using tuna as chopsticks. So she's kind of, I eat sushi with tuna as chopsticks. So this is a PP attachment problem because this PP phrase should be attached to the noun sushi instead of the verb eat. So that's two typical problems. One is the word sense, and the other is the structural ambiguity. And if you're more imaginative, you can even get this. Basically, you can imagine you're doing scuba diving in the Caribbean, and there's a school of tuna around you, and there's sushi flowing in the water or dropping off from the sea, and you're competing with them for eating sushi. So here, you're doing the PP attachment still to the verb eat, but you're interpreting the with as together with, instead of using something as a tool, something like that. So there's a bunch of ambiguities. So what we can say about this little kid? Well, Aaron said your search algorithm is biased. There's no way you can get this or that as your optimal solution for this sentence. So OK, let's go back to this sentence. I saw her duck. There's apparently actually a third interpretation where the duck is kind of a verb as bent. And what about I saw her duck with a telescope? Then you can have 6 because you can attach this to the verb or to the noun. And what about I saw her duck with a telescope in the garden? Then you have even more. And as your sentence gets longer and longer, you have many, many more. And that grows actually exponentially with the sentence length. So here's the first problem that why NLP is hard, because we're searching over an exponentially many candidates in the search space. For example, like this. So the solution here is very simple. We just do a locally factored space and do dynamic programming on a small space. And that is called packed forest, which I'll cover in a couple of slides. And algorithms like CKY and Viterbi are all instances in this framework. But the difficult part is to incorporate non-local information in this framework. For example, the saw with telescope is kind of likely, so you should attach this with telescope to the saw instead of to her duck. But this kind of long distance and non-local dependencies, and so is eat sushi with tuna. You know that sushi with tuna is kind of nice and likely probable co-occurrence, but eat with tuna as chopsticks is really non-likely. But this is really non-local and long distance. So the key question that we're going to address today, and it's really hard problem in NLP and all the other fields in CS, is how do we incorporate non-local information in the search, and how do we do it efficiently? So there is apparently an easy solution that is pipeline reranking or rescoring. So we first postpone disambiguation by propagating a k-best list instead of one best, because we know that one best is not guaranteed to be the best in later stages. And later stages have more access to more global information like long-distance dependencies. So for example, we do a tagging, and we postpone the k-best parse tags sequences and do parsing, and there is k-best parses feed into the semantic interpreter or semantic role labeler. And that's apparently what we do in our field. But the question here is we need very efficient algorithms for a very large number of k, for like k equal 1,000 or even 10,000 for MT especially. That's the first solution, but that's not the principal solution because it's kind of two-staged, and we really want to do a joint version, which you already integrate non-local information directly into the search instead of kind of doing a re-ranking. So this is more likely to get the solution, to get the best solution. But apparently this is NP hard, so it's intractable, and we can only do approximation. But how do we do it in a principled way? That's a largely open question, and we're going to address this question in this talk also. So here's the outline. I'll first briefly review the packed forest and the hypergraph framework, and then we're going to focus on solution 1, where I develop exact and fast k-best search algorithms in the forest. And then we use these algorithms and extend it to solution 2, where you do approximate joint search with non-local features directly into the search space. And I'm going to first talk about an application in parsing, discriminant parsing called forest reranking, and then apply both these two techniques to machine translation and focus on the problem of decoding with language models. OK, so any questions? Do stop me if you have any confusion. And OK, packed forest. So packed forest is just a compact representation of exponentially many parses in the polynomial space. So for example, you have sentence, I saw him with a mirror. Apparently, there are two readings. Either you can attach it to the noun and forming a bigger noun, and then it combined with a verb. That's the dashed lines. Or you can just directly attach it to the verb and combine it with the ternary combination. That's the solid line E1. So these little things, like VP16, are called nodes or items in the deductive parsing framework. And these guys, which combine several nodes into one node, are called hyperedges. So this is really a structure of a hypergraph. And each hyperedge, like this E1, is just a instantiated deduction. Say, for example, E1 is saying, if you have already derived VBD and MP and PP, you can also derive VP for the combined span. So that's just very simple as just CKY or the famous algorithms. That's nothing new. And if you are coming from the speech or lattice world, you're familiar with the lattice, which also encodes exponentially many paths, but we just extend it to exponentially many trees. So basically, this is a graph world, and this is the hypergraph world, where we extend from regular grammar to CFGs. So you have state transitions from one state to another, and here we combine several kind of states or nodes into one node, and we can deal with the hierarchically branching stuff like tree structures. So that's just a very simple extension, and you should be familiar with that. OK, so but because we're doing optimization, we're doing like one best or k best, we have to have some way to measure the comparison, right? So how do we do it? So we have a weight function for each hyperedge. Like in CKY, the weight function is just FAB. When you combine from smaller spans to a bigger span, the result is the product times the probability of this rule, so that the probability of rules will accumulate towards the root. So, but a crucial restriction is that we require each weight function to be monotonic in each of its arguments. For example, here, this FE is monotonic in both A and B. So why is this important? Because it is exactly encoding the optimal subproblem property that is required in doing dynamic programming. So for example, it says if a bigger problem A, sorry, I just use this. A big problem A can, if you claim the optimal solution is to decompose it to smaller problems B and C, then the small problems, the sub-solutions for B must also be the optimal. Because if you have another solution B prime, which is you claim to be better than the B, then by applying this monotonic weight function, you can always get a better solution for A, the bigger problem as well. So it says optimal solution must be optimal everywhere. And when we have this property, we can do inference, we can do dynamic programming efficiently. So the basic operation in the hypergraph is basically an update along a single hyperedge. So if you have a hyperedge connecting U to V, then you can use the result of, use the weight of whatever score in this node, apply this weight function, and to compare with the current estimate of this V. And if it's better, so this plus is a comparison function returning the better of the two. If it's better, you just update the value. So you're going to see the how do we do the one best, very simple one best inference in a hypergraph. So this is called generalized Viterbi because Viterbi is defined on lattices, and we just basically generalize it to hypergraphs. So, but it's very simple. It's just nothing different. So we first do a topological sort, which assumes acyclicity. So Viterbi can deal with direct acyclic graphs, or DAGs, and we do direct acyclic hypergraphs. And when you have this order, you just visit each node in the topological order. Basically, in CKY, it's bottom-up order, like you combine from smaller spans to bigger spans. And you simply do an update on each hyperedge that comes into this node. So for example, you do this, you apply this wave function FE to the result of these two antecedent nodes and update on the DV. And you do the update on each of the hyperedges. And why is it correct? Because it's very simple, because by topological ordering, when you do this update, all these antecedent nodes must already be being fixed for its optimal answer. So they're safe, and you don't need to do any cyclic updates. So that's why it's kind of efficient. You don't do any waste of time. And the time complexity is simply linear in the number of hyperedges, that is the E, because you did once and only once. And that's exactly why CKY parsing, the famous algorithm, is n cubic. N is the length of the sentence, number of words in the sentence, because there are exactly that many hyperedges in the hypergraph. Any questions so far? OK, so we're going to now extend it to the k-best case for doing reranking or rescoring for very large k, because we need really fast algorithms. And we just laughed at this little kid who got this IE sushi with tuna as chopsticks. But actually, this is also the one best parse from our best parser in our research community. So that's exactly, I checked with the Charniak parser, and exactly it returns this, basically attach the PP to the verb. So it kind of Charniak also uses it as chopsticks. So we're going to fix that, and we're going to incorporate NonLocal features in k-best parser. So the correct parse is actually the second best parse from Charniak parser. OK, so the most naive way to do k-best is to say, well, we want the top k for each node. So we replace the single value by a vector of k, so that AK, for example, A1 is the best answer. And if we keep them sorted, A1 is best answer for U1, and AK is k's best answer for U1. And for the consequent node V, we also have the top k. So now the question is only, how do we apply this wave function to two vectors instead of two numbers? Well, there are apparently k-squared possibilities if you do it naively, right? Because every AI and BJ is a possibility, is a combination. But if you do it naively, you have to enumerate everything, and that gives you k-squared for each hyperedge. And that's really bad, because k can be 1,000, and k-squared can be terrible. But that's really stupid, and we can do it a little bit better, because the key insight is we do not need to enumerate the whole grid, the whole square, because remember that A's and B's are sorted. And also because the weight function is monotonic. Remember, the monotonicity is a very important property here. So we can conclude that this corner, A1, B1, must be the best among the grids, right? And that's very simple. But what about the second best? Well, it's either this guy or this guy, right? And what about the third best? If you just keep a frontier and you say, OK, the second best must be among these two guys. And if this guy's really a little bit better, then you got this. So the third best must be coming from one of these guys. So you keep a frontier, which is a set of candidates for extracting the next best. And in each iteration, you just simply extract the next best and push the two successors, right? And the two successors are basically just, if this is ij, and it's I plus 1j and ij plus 1, the two ones on the shoulders. So that's very simple, and you can do a binary heap or whatever Fibonacci heap for this priority queue, and that gives you k log k for each hyperedge instead of k-squared. So that's huge speed up, because k can be huge, but still too bad, because if you can do this. Still too bad, because this works on each hyperedge sequentially. It kind of speeds up the amount of work on each hyperedge significantly, but at the end of the day, we're not interested in the k-best out of each hyperedge. We're only interested in the k-best of these nodes, right, as I said. So how do we do it? We kind of want to process all these hyperedges in parallel, right? And we can do it in one shot. So basically, we can just extend it to multiple hyperedges. Basically, the frontiers would now spread over all different hyperedges. and they would initially be just the left corner of each each cube, or you can be a hypercube if you have more than binary combinations, or it can be a high-dimensional cube. So initially, it's just what the leftmost corner of each cube, and then you kind of push the successors and extract best, and so that you just basically do algorithm 1 simultaneously across different hyperedges. And that's basically doing locally Dijkstra because this is kind of best first expansion. You can imagine water coming from the leftmost corner and kind of flows towards this corner, right, in a best first way. But globally, it's still Viterbi in the sense it's bottom up in the topological order. So it's a kind of weird combination of Dijkstra and Viterbi in this sense. And this gives you dramatic speed up because you can do for each node instead of for each hyperedge. And this is a multiplicative overhead for each hyperedge, and this is kind of additive instead of multiplicative. And E is much bigger, the number of hyperedges, than the V number of nodes. So in real practice, this E part is going to dominate the computation. And that's so this is much faster than this, as we will show in the experiments. But still not quite yet, because in algorithm 2, we still compute the top K for each node, while at the end of the day, we are only interested in the top K of the whole hypergraph, or in a sense, the top K of the final or goal item, or the final node, right? So why do we waste time computing the K best of any intermediate nodes, right? So we really want to do kind of laziest approach, which computes as many as needed for each node. So it's not a fixed K for each node. It's like you can compute 3 best for this node and 10 best for that node. So it has 2 phases. The forward phase is the same as 1 best Viterbi, but the only difference is we store the forest along the way. So normally, if you do CKY or Viterbi, you just keep the best back pointer, so you can retrack or whatever, backtrack the best derivation. But we also keep the alternative hyperedges, the ones that are non-optimal, so that we can recover the second best and third best as we go on, right? Because we're really interested in them. And the backward phase will start by asking, what's your second best to the top node, to the root node, and then recursively propagating that question. OK, so here is an example. So this node is the root node of the whole sentence. And suppose it has 3 hyperedges. And after the first forward phase, you already know which is 1 best. But that's the only thing you know. So you know that this hyperedge or this combination is the best way to derive this node. But now you ask the question, what's your second best, right? And by algorithm 2, it must be either this or one of these two, because these 2 guys are the successors of this node, right? So you kind of just do the same thing. But the question is, you don't know these 2 guys, because these 2 guys are kind of combining the second best of this guy with the first best of this guy, or second best of this guy with the first best of this guy. But they don't know the second best themselves, because every node just knows it's 1 best. So you kind of propagate this question, what's your second best to the parent nodes, and they would propagate to their own grandparents and so on. And the recursion goes on to the leaves, and you can propagate back the numbers here, and you can proceed, right? So if you ask for more, like what's your third best, it'll keep asking, right? So basically, it's kind of varying the amount of computation at each node automatically, so that if this is really ambiguous node, I kind of do more work on it. If it's less ambiguous or more certain, I do less work on it. So kind of automatically adapting. And here's the summary. So if you observe the progression from 1 to 2 to 3, we become lazier and lazier. And we do more and more computation on demand. So we kind of don't want to waste time. And we're working on a larger and larger locality. For algorithm 1, it's a hyperedge by hyperedge basis. Algorithm 2 takes all hyperedges into 1 node simultaneously. And algorithm 3 is kind of globally on the whole hypergraph. And the time complexity improves to from this really bad to kind of E plus D. D is the length of derivation. And here is the size of the tree. And the size of the tree is just linear in the number of words. So E is, in CKY, it's cubic in the number of words. So this is much larger than this D part, and it's going to be dominating the computation. And this E is the amount of work you need for 1 best anyway, right? So you can't do anything better than this E. So the only extra work is something like this, which is very small, unless the K is huge, right? So in practice, you're going to see that E is still dominating. So we're going to see some experiments. So this is statistical parsing. So the best, or not best, the state-of-the-art calling speak-out parser. And we implement 0, 1, 3 algorithms on it. Not 2, because when I have 3, I thought 2 is not going to be as good. So this is the average time, parsing time for each sentence. And this is k from 1 to 10,000. So this is log. So this is much worse than it looks like, right? And we can see that 0 is much worse than 1. But algorithm 3 is so fast that it's almost just flat. In the sense that if you want to compute 10,000 best parses, it's just not too much different from computing the 1 best. Why? Because the complexity already tells us that it's E plus D times k log k. And D is much smaller than E. And for lexicalized parsing, E is even higher than cubic. So unless you have a huge number of k, this part is still going to dominate. I mean, that's just this 1 best part is still going to dominate the whole computation. Sure.
So I'm pretty sure you got this question before. People in speech have been using something similar for extracting n-best from edge of matrices. So what you do there, you do a forward pass, Viterbi pass, and then you do a backward pass using an A-star search. And the look-ahead function is exact because you're not estimating anything there. And you can keep a stack that is as deep as the number of hypotheses you want. So you will get pretty much the same time complexity. I would have to look at it, but I'm pretty sure it's very similar. Did you look into that? Or?
Yeah, as several people have been telling me this story, and it looks like there's even a way to combine the two in the sense that we are not using the A-star estimates in the backward phase. So I would suspect there's even more improvement on algorithm 3 if we combine that technique. But the general idea is very similar to the lattice world, to the speech literature in early 90s.
So it is similar.
It is similar in general, yeah. But I guess there's still room for improvement if we kind of combine, we kind of use more ideas in that work. Okay. Yeah, but general idea is kind of the forward phase and backward recursive phase is very similar. Okay, so this is a oracle curve. So oracle means if you have an oracle that can select the candidate in the n-best list that is closest to the correct parse or golden standard parse, then what's your potential, like what's your highest number in the n-best list? This is kind of saying what's your potential of real reranking, because in real reranking time, you don't have access to the gold standard. But if your oracle is high, then you have better chance to get better results after real reranking. If your oracle is already very low, then there's not too much room for improvement. So this is measuring the quality of the k-best list. And we compare it with previous work on Collins 2000 parse reranking. So this is on exactly the same parser. And this is k to 100, and this is the possible score. So 1 best is really low, and if you include more and more parses, you kind of have the potential to go very high to 97. But our algorithm is much better than Collins' algorithm, which turns off dynamic problem totally. So his search is not a principled one. And as a result, after k equals 60, his curve doesn't even improve. And intuitively, as you have more and more parses, you would expect you have a better chance to get closer to the oracle, right? Although the chances are smaller and smaller as your k grows because this curve is really logarithmic instead of something linear. And that makes sense because your k, the number of interpretations, should grow exponentially with the sentence. So this is kind of hitting diminishing returns here, right? Although it's kind of still increasing. So this is really the problem of this approach, or the solution 1, that is pipeline reranking, that we really need exponentially big k, and we cannot afford that, right? So if you have a fixed k or a smaller k, it is going to kind of be a limited scope. So that's why we want to do solution 2, that is to do the joint search from the start, from scratch, to integrate non-local features directly in the search space instead of doing k-best, the two-stage approach. And we're going to do it for the same re-ranking task for parsing. Okay. So we don't want to do this because, as I said, there are too few variations in limited scope, and that case would become worse for longer sentences. Question?
So what if you do like 10 times more than 30K? What's the number for that correct passes?
That I don't know. This is kind of the complete match probability, complete match accuracy for the Collins parser. And right, I don't have that number, but as you see, the general trend of these curves would grow logarithmically as k grows, because you would expect that you have exponentially have to like double the k to just see one more significant change in the list, right? So yeah, this gets worse and worse for longer sentences, and it also has too many redundancies because the same subtree got repeated many times over different parses in the mbest parse and the mbest list, because you have to enumerate everything in the pure mbest list. So that's a naive approach, but that's really bad. And so, for example, a 50 best list, which people usually use in our community, just typically is just a combination of 5 to 6 binary decisions, because if you blow the exponential up, that would be this. Yeah, so this is really bad. So you really want exponentially higher number of k, and we cannot do that. So we want to do re-ranking on a forest, but with non-local features. With local features, it's totally easy as just CKY, and people have done that, a bunch of people, and very successful. But what's really interesting is the non-local or long-distance dependencies, as we saw that you do with the telescope. So and we can only do it approximately. So we do a very simple scheme, which is called on-the-fly re-ranking at internal nodes, in the sense that conventional re-ranking is re-ranking on the top k of the final node or the whole global thing using kind of algorithm 3 idea. But we kind of want to use the algorithm 2, kind of back off to algorithm 2, where each node has a top k solution or derivation. So this kind of just algorithm 2. And we want to keep them ranked so that the external non-local features would already be sensitive in sorting or ranking the mbest list in the internal nodes. So not like wait till the final node, because something, if it's bad, we can already get rid of away, right? So it's kind of using the non-local features as early or as early as possible, and use it as many as possible at each node. And it's kind of a combination or a step towards the unification between traditional chart parsing, bottom-up chart parsing, and discriminant re-ranking with non-local features. So kind of combining these two lines of research. And for simplicity, we're going to only use perceptron for re-ranking, which is shown here. So for each sentence, S, we have a set of candidates, which is either in best list or a forest. A forest is just kind of implicit set, right? So it's either explicit set or implicit set. And we have an oracle, which I said as the closest to the golden standard. So the learning algorithm is going to learn a feature weights that can magically pick a better parse in the set of candidates. So we have a decoder. So the perception algorithm just makes several passes through the whole training data. And for each example, SI, you do a decoder that selects the best parse among the candidates using the feature representation and the current weight setting. So this part, argmax operator, is called the decoder, which is the difficult part in this work, and we're going to talk about it. And if it's not the same as the objective, which is the oracle tree, we're going to do an update, right? So as this goes on, the weight vector will get better and better, and hopefully we can get a better get a candidate after re-ranking. So that's the general idea. And the feature mapping, that is basically a function of each feature is a function that maps a tree to a real number. And the first feature is just the log probability from the generative parser, like the baseline Chanya parser. So that's very simple. And every other feature is an integer value feature, which is basically counting. So for example, this rule S goes to MP BP period appears once. So the value of this feature is 1, and the value of this feature is 2 because it appears twice. And these are instances of rule feature, and we have more features like that. Questions? No? Okay, good. And a crucial difference between mbest re-ranking and forest re-ranking is that we have to distinguish the feature set. As we recall, for mbest re-ranking, you don't need to do anything about the features, and you can define arbitrary features, and they make no difference to mbest because you just compute it on each individual sentence or individual tree. But here we have to make a distinction between local and non-local features. Local features are those that can be computed in the factor space. Basically, it can be computed among the local productions, and it can be pre-computed or stored in the forest, right? And non-local features are those that spans across several different hyperredges. For example, the parent rule. So this is a rule, it's local. Parent rule would add the the grandparent non-terminal, and that becomes non-local because it spans across this hyperedge and this VP hyperedge. So it's kind of across two hyperedges, and it's now non-local, right? So a better example, word edges. So word edges is saying that you include the label of this node and the length of the span and the two surrounding words. Is this local or non-local? How many people think it's local? How many people think it's non-local? So the answer is actually it's local. Why? Because the input sentence is fixed. And in discriminant models or conditional models, we are not generating the input sentence or the input. We're only generating the hidden tree structure. So the whole input sentence is taken as fixed. And you can draw features on the input. That doesn't matter. And everything else, like this node and the label of this node and length, is already encoded in this node. So everything is either encoded in this node or on the fixed input sentence. So that's local. That's good. So this looks very complicated, but it's still local. But if we replace it with the part-of-tree tags, is it local or non-local? So now it becomes non-local because these guys, part-of-tree tags, are treated dynamically generated in the parser. So it's not like we are using a external tag or we kind of generate them on the fly. If we do it on the fly, it's non-local. So these guys are non-local. But the good news is that the majority of our feature set is local. So that's kind of interesting, and nobody have looked into this kind of distinction before. But the crucial question is for non-local features, because local features we can already pre-compute on the fly. So for example, the parent rule non-local feature, so what we're going to do with them, so we basically do a bottom-up, and we compute as many features or as many partial values as possible at each node. So for example, this feature cannot be computed at this MP node, but can be computed, is going to be available at this VP node because it has access to the subtrees. And if you go up, from bottom up, you can compute this feature at this S node and this feature at the top node. So basically compute the unit instances, that is, as many instances as possible you can compute on this node, but not computable at each of the subtrees. So for those that can be computed on the subtrees, like the S subtrees, you should already compute it. So, and leave those you cannot compute to your parents. So every node should compute as much as possible. That's the idea of kind of on-the-fly computation of features. So features have to actually factor across nodes. And so at each step, at each node, there are only very little like kind of derivatives of each individual feature. And you just sum up the kind of derivatives or unit instances at each node. So this is a better example. N-gram tree, that is saying for each pair of consecutive words, like boy with, what's the minimum tree fragment that can cover this? So this feature should be computed at the smallest or lowest common ancestor of the two, right? In this case, the VP node. So the unit instance of this combination, like if you combine from B and C given an A, is just between the boundaries, just the two words on the boundary of the two subtree, right? So the only instance is this guy, and everything else, like here J plus 1, is already computed in the C subtree, and this guy, like everything here, is already computed in this B subtree. So only work is this actual work is here, except that the leftmost word and the rightmost word is not computed because they should be computed when this A is further combined with some other guys in the future, then you can combine on the boundaries, right? So you leave things on the boundaries, but you combine the things on your subtree boundaries. And for example, you do bottom up, and when you are at this MP node, you compute this guy. When you're at PP node, you compute the boundaries, the words on the boundaries of the two subtrees. That's this guy and this guy. And when you're reaching the VP node, you have three subtrees, and the cases on the boundary are sol, the, and boy with, that is the pairs on the boundaries between the three subtrees. And the only unit instances are these two guys for this VP node, right? So you just basically kind of sum up all these little unit instances. So at each node, your work is kind of small. And heads is another example of the non-local features. So we basically propagate the heads from bottom up. So each node is annotated with the head. And the only So we have the head modifier relationship, the lexical dependencies, like in bilexical parsing. The only unit instances at each node, let's say at this VP node, is between the head word of the head subtree and the head word of non-head subtrees. So it's only between saw the and saw with. Anything else, like the boy, should be computed at this subtree already, and with telescope should be computed with the PP subtree already. So the only extra work you're gonna do is between kind of the shallow level between subtrees, right? Any questions? Good. So how do we do decoding with non-local features? Using the same idea of algorithm 2, but now you have, say, for this B and C combination, you have 3 guys for B and 3 guys for C, and they are sorted. But the difference is that you now have a unit instance, or the non-local features, as a result of a combination, right? And for example, the score is 0.5 for combining these 2 guys. And you cannot predict this part, because for something later here, so the second best of this guy, maybe when you combine it, it kind of fits better, right? And you cannot predict. So it's not going to be the case that this whole grid is totally monotonic, or this guy is going to be 1 best. But sometimes maybe something later can get even better. So it's non-monotonic, and you get something like this. This guy is actually better than the leftmost corner. So, but because the non-local features are only the unit instances, they're considered to be small and not affecting the whole thing in a larger scale. So we can still say this is almost monotonic, but kind of distorted locally a little bit. It's not totally monotonic, but it's kind of like this. And you can still apply the algorithm 2 and just as if it's monotonic, and you just still do the best first. And the hope is there is search errors, but not too much. And if you enlarge the beam to counterbalance the search error, you'll still get a better trade-off. So you still do algorithm 2, and you kind of have a frontier, and you got pop up things, extract things out of order a little bit, but you sort it after the extraction. So you can do it across hyperedges, just as in algorithm 2, right? Very simple idea. And that gives you a significant amount of saving in computation. So here are a little bit of results. So if we do it on top of Chanya parser, and I modified it to dump a packed forest for each sentence, that turns out not to be actually quite trivial. So we can plot the oracles of forest, we call it forest oracle, compared with n-best oracle. So n-best oracle, this curve we are seeing this kind of going very, very slowly, logarithmically, as n grows larger. But the forest curve is, first of all, much smaller in size. The size is the average number of hyperedges or average number of productions in n best list. So the size are much smaller. Why? Because we're compact, right? We kind of share common subderivations in forests instead of kind of spell them out in n best lists. So the size are much smaller, but still we get much better oracle scores because we have more variations. So for example, if this is with different pruning factors, so we can prune it very harshly or prune it very aggressively or whatever. So the common baseline people use in n-best ranking is 50 best, and it's 96.8. But the point we're going to use in this work is 1 point higher in terms of possible score than the n-best. Okay, so this curve looks much better than this kind of flat curve. And if we do real reranking, so these 3 lines are the n-best reranking baselines, and this is the forest reranking. So in both cases, you can either first use only the local features and then add back all the features. Okay, if you just use local features with n-best, like 50, you can get something like 91. And if you add back all the features, you get something like 91.4, which is the state of the art. This is currently the best in literature. And the pre-computation is the amount of work for feature extraction on the n-best list, and the time and the space. And training is perceptron training. The rounds are determined by the depth set. And here's the average time in terms of hours for each round, for each iteration. So, and I was interested in asking the question, if you double the size of the n-best list, how could it be? How better it would be? It turns out it's only 0.04 improvement, because as you see, this grows extremely slowly as you kind of hitting the diminishing returns. Although this grows like, this improves 0.4 from 50 to 100, the real re-ranking only improves 0.04. right? So really, that's the reason why people didn't do higher re-ranking in practice in our community, and almost everybody does 50 best because, well, another reason is this guy is going to be less practical because the file size is huge. I mean, not for Google people, but for academia, and we don't have like for clusters, you have problems of distributing the work. Although this part can be parallelized, but yeah, so this is becoming less and less practical as you get higher and higher n. But for forest re-ranking, if we only have local features, the decoding is fast because it's exact decoding, and we got something better than this. But if we include odd features, the decoding slows down tremendously. But this whole part can still finish in 2 days. And we got much better, like 91.7, much better than the current best accuracy in literature. So the whole thing is implemented in Python. So it's kind of considered to be very slow if you do it better in Java or C. But it's kind of still OK, and it scales to the whole tree bank, not like just for short sentences. So the whole tree bank of any sentence length. So if you put it in perspective, so this is all the other best performing systems. D means discriminative, G generative, S is supervised when you have extra non-local unlabeled data. So the whole thing up to this line is trained on tree bank only. And for this comparison, we got the best to date accuracy on the Penn tree bank. Although this guy gets a little bit better with the extra unlabeled data. But the techniques used in these two work are orthogonal. And they do have an n-best re-ranker as part of their pipeline. So if we replace it with the forest re-ranker, there is hope that this can probably get even better. Let's just hope. OK, so we have covered the parsing part, and we're going to briefly talk about MT, basically doing the same techniques on decoding with language models. OK, so here's just the architecture. I don't want to spend too much time. Everybody knows better than me. So there's a translation model and language model. And if you only use translation model, you get a bunch of candidates, and you use language model to rescore it. And that's called, you can use algorithm 3, which you can efficiently generate very large k-best list. And that's what ISI and other CMU people do, like for 25,000 best rescoring and so on. But that's not what we want. We want to kind of a joint decoder, which integrate n-gram models with syntax-based or phrase-based models. And what we're going to do it is still representing it as a Pack forest, and these guys, n-gram models, as non-local information, just as we saw before as the non-local features. And this is kind of forest rescorer, kind of much faster than before. OK, so a little bit background on syntax-based MT. So we have a synchronous context-free grammar for generating pairs of languages. Right, because we have a CFG for one language and we have CFG for another language, and we couple together, we got a synchronous CFG. So this rule says between Chinese and English, the PP and VP are swapped. So we always say PP, VP, and you guys probably say, hi. Sure, question? Huh? Sorry, OK. Is there a question in the other room? No? OK. So it says that PP and VP are swapped between English and Chinese. So this is the Chinese version of held meeting with Sharon. We basically say, with Sharon held meeting in our language. OK, so how do we do it for translating from Chinese to English using this synchronous grammar? Well, that's very easy, just not too much different from parsing. So basically, you project the grammar to the source side, you get a Chinese grammar. So this is a Chinese CFG, really. Use this Chinese CFG to parse the input sentence, and you got this tree structure. And the only extra work is to recover the English side, and that's kind of this with Sharon held to talk. And this rule says you have to swap it on the English side to generate held to talk with Sharon. Right? So that's just the same as parsing. But the key question is, how do you add a language model into it? And language model is really important in translation quality. So you can do it exactly using dynamic programming still. You basically split nodes into LM instantiations. For example, VP36 is now having a lot of different instantiations depending on the boundary words on the English side. So for example, VP36 held talk or VP36 hold conference would be considered different now, right? Because your state space is kind of split into a lot of more fine-grained level. And when you combine it with the other guy, you can score the bigram pair, which is still on the boundary. Remember, again, it's on the boundary between the two guys. And then when you combine it to S, you still remember the two boundary words, which will be further combined with the other guys here, right? So every node now remembers the two boundary words. I mean, in phrase-based world, it's just one boundary word added on almost the rightmost, because phrase-based people generate monotonically from left to right, but we kind of do kind of arbitrary reordering in the syntax tree, so we have to remember the both boundary left and right. But that's really bad because it's going to blow up the search space, right, tremendously. So we're going to say do a little bit beam search, keep at most k kind of LLM instantiations at each node. But how can we do a little bit better using algorithm 2 or this kind of algorithm 2 idea? So we see this grid again, and the numbers are the same. But the only difference is now these blue numbers, the non-monotonicity part, is now phrased as LLM combination cost, basically the combination between the two guys when you combine it, kind of LLM combo. For example, this 0.5 means the bigram probability between meeting with is 0.5. And these are the three instantiations for VP and the three best instantiations for the PP, right? And you say something like talk with is even higher probability, more likely than meeting with. So this guy probably is having the chance to get better than the one best. And this is going to be a little bit non-monotonic. You do it still as if it's monotonic in algorithm 2 across all different hyperedges with search errors, but as we will see, the search error is worthwhile. No, sorry, the compromise is worthwhile. And here's the result on Faro, the phrase-based decoder. So, so if we implement algorithm 2, Q-pruning, into Faro, this is going to be much faster. And how do you measure it? We measure it by the blue score and the number of hypotheses explored for each sentence. And you can see at the same level of blue score, we are about 100 times faster. Or you can see if you have the same amount of time, we're kind of much better than blue score. So it's always like when we have the same search quality or the output quality, what's the speed up? Sure.
What's the reason why the blue curve goes down?
Right. So the parameters are not. The parameters are kind of tuned for the Faro, and our implementation of Faro is not like it's almost exactly the same, but with small, very little differences because there's something hidden from their manual. But I know what's going on. I mean, in detail, I can tell you offline. So there's a little bit extra thing in Faro's implementation that's not the same as our kind of vanilla implementation. And it turns out to be a little bit different for this parameter setting. Okay, if we retune it for our system, it'll be kind of different. Okay, so this is another syntax-based system, a tree-to-string system, which I can talk about in detail if you guys are interested. So you can use algorithm 2, and we can also use algorithm 3, which is even better, kind of not fixing the k, but also let a k vary for each node. That will give you even better speed up. But in general, kind of the big speed up is from algorithm 2 to the naive guy. So this is the conventional beam search, and we still got like orders of magnitude faster in both syntax and phrase-based systems. So okay, so a little bit of conclusion so far. So we have a general framework for doing dynamic programming on hypergraphs and focusing on the monotonicity, which gives us exact one best algorithm and exact k-best algorithm very fast. And when there is no monotonicity, kind of a little bit non-monotonic, when we include non-local features, we can still do it approximately. And we discussed two special instances, two particular instances for discrete parsing or MT decoding. And in both cases, we got orders of magnitude faster than conventional approaches. And also for the parsing case, it kind of makes possible for discrete parsing training of the whole tree bank. And it gives us the best tree bank parsing accuracy to date. And these algorithms have been implemented in almost all state-of parsers and almost all major MT systems, like the best phrase structure parser, best dependency parser, all the other best performing parsers, DLP parsers, syntax-based systems in list evaluations, and also phrase-based. Okay, so a little bit of future directions. First is further work on this forest reranking, because we see that forest reranking is still much slower than MBEST. Although it's doable, but still much slower. we're going to do a little bit of algorithmic issues like inter-sentence level parallelization, because perceptron is harder to parallelize in the vanilla kind of setting, although it can be parallelized in like batch perceptron or something like that. But if we really want to stick with vanilla online algorithm, we can still parallelize the work for each sentence in the sense that if you think of Viterbi on a lattice, a lot of nodes doesn't have precedence with each other, so they can be actually parallelized. And it's the same for CKY or these kind of forest space algorithms. A lot of things are not interdependent, so they can be parallelized. And I kind of want to do this. As we have more multi-core in academia, or you have the guy who has thousands of machines here. And combination with semi-supervised learning, as I already said, that can utilize extra unlabeled data to get even better accuracy and deeper decoding, probably including semantic rows. And as a machine learning algorithm, because perceptron is really kind of very simple vanilla thing, and there's Myra and the other algorithms which has better performance. And what is missing here is theoretical and empirical analysis of search errors in this non-monotonicity setting, because we only have kind of speed up or the final end-to-end performance, but there's no kind of in-depth analysis of the search error. And for MT, we can still do this non-local features for reranking on forests. So people have done this on local features on the phrase-based systems and showed modest improvement, but this is really slow. And we want to use it for syntax-based system like tree-to-string, which is fast in linear time decoding. And another story similar is happening already because we can use it, a packed forest for tree-to-string decoding, in the sense that, so tree-to-string decoding is basically using the one best parse tree from a parser and does the kind of recursive rewriting. And we don't want to commit to the parsing errors or the one best trees, so we can use a packed forest. This is already done, and shows like 2 or 3 proof points better. And we can also do generation or summarization, whereas the non-local constraints can be phrased as non-local features as well. So that's basically it. So I'd be happy to take questions.
Can you go back to the parsing results?
Oh, sure. Wait. Here?
So the gain from the local on top to the local on the bottom, so that's due to that there's just a better basic search now.
So you mean local versus local?
Right, right.
Yeah, I guess.
So would it be possible if you would just use that better local search and just do 100 best list on top of it, that you would get the same gain also with all the features? So because the gap basically is there 0.25%, and then if you, on top of that you would just use a normal 100 best list, what would be the gains there? Did you?
Oh, sorry. You mean using local for 100 for mbest?
But using the local on the bottom.
On the bottom, for forest.
Right, and then you would just extract 100 best list based on that kind of search. That should give different results, right? Because the first best result is different.
Sorry, I don't understand your question.
So there's a difference between the local on top and bottom, and the difference is search.
Yes, because this is using forest, this is using 50 best list.
Right. And based on the forest, you could extract. Okay, I see. Okay, I misunderstood. My question doesn't make sense. Sorry.
So at some point you mentioned that you do part of speech tagging as part of parsing.
In part, yeah. So it's kind of
useful, or is that?
Yeah, of course. Because if you do it using an external tagger, then it kind of gives you only one best sequences, and there's tagging error, and you cannot recover it in the parsing. So
but you saw that it makes a difference to the final parsing.
So that doesn't happen. Well, we didn't do that in. So people don't do that for phrase structure parsing. All the major parsers does parse tagging internally, meaning dynamically. For dependency parsing, like the state-of-the-art McDonald parser, they would assume a tagger, external tagger, so they would take both tags and words as input. So that would really commit to tagging errors, and we would. So there is hope that we can use non-local features so that we can do tagging on the fly for dependency parsing as well. So there's really so Ryan told me there's kind of at least 2 points difference if you just do the parsing on gold standard tags. So that's kind of very significant error. Yeah.
Have you run translation experiments with a trigram?
Yeah, these are all trigram, not background. So, but
you only keep one word of context, right?
But no, if we would do trigram, we keep 2.
Okay.
2 words on left, 2 words on left, right.
And what is the effect of search errors on K, or effect of K on search errors?
Effect of K?
Mm-hmm.
So these graphs, I think, are, you mean something like this? Like what's the K here? I don't remember, but not too big, like 20 or 30 or 50, not too big. Yeah. So this is like increasing K, you get better and better scores, right? But there's search errors compared to the conventional approach.
Sorry.
Sure.
So, I mean the x-axis average number, that really you obtain that by changing K.
That's the search amount of computation you did for each sense.
Right.
Right.
So
yeah, exactly. Yeah, changing K. Yeah.
So just you don't have the K's associated.
Right. Exactly. Yeah. So this may be K equal 2. This is maybe 5. This 10. Maybe 20.
Yeah.
Something like that. Yeah. Right. So actually, I have a better graph for the search errors. And so the same graph would be translated here. That is the model cost instead of blue score. So kind of an internal search error measure. So blue score is kind of external, and it's not really sensitive to search quality. So if we really care about search quality, how many search errors are we making due to the approximate search? And here's the result. So it's still like 30 times faster, and these points are using the same beam, basically. So this is a conventional beam search. This is kind of algorithm 2 Q-pruning beam search, and this is like K equal maybe 2 or something. This is like maybe 5. So you can see that in individual settings, we have a lot of search errors, and we are much faster. But it doesn't make sense to compare points to points. It only makes sense to compare curves to curves. If we are at lower left corner, we are better search.
Sorry, I'm a little confused. What do you mean? So when you say a search error, you mean your models will assign a higher probability to the hypothesis,
No,
another hypothesis than the one that you
right, exactly. So it should have returned something here, which is say 84, but it didn't get it. It kind of missed it in the search, and it returned something much worse. So here's the lower the better. So if your search is approximate, it kind of missed the optimal area or the very good area which you would expect to.
And do you know how much impact this has on the blue score?
Yeah. So
if you were to get the correct sentence, how much your blue score would go up?
Yeah. So this graph is the same as the other graphs. So just everything the same. Just we changed the y-axis from model cost to blue score, and so the graph I showed you previously is. So this graph and the previous graph are basically the same, except that we changed the blue score, the y-axis. So basically, we got an even higher amount of speed up if you only care about blue score. In a sense, blue score is not that sensitive to search errors. Right? If you compare search errors, it's just like 30 times faster.
And what's the difference of using a bigram here instead of a trigram?
That I didn't do because all the experiments are trigram. But you can do higher order.
Because I would use a lot less memory, right? Because
yeah, I would expect that higher order n-grams would even get higher amount of speed up.
But you'd use a lot more memory because the recombination isn't as good, right?
Why?
Because the recombination isn't as good? Is that true? Or to get the same levels? Or?
No, it's just going to introduce more search errors, I guess. But
using
higher order, yeah. But it doesn't affect memory.
Okay, I guess, yeah. So either you can get more search errors or use more memory.
So in machine translation, where you use like really large language models that are like on servers, what really takes time is the amount of queries that you would make to the server.
Right.
Basically, the number of batch queries.
Right.
So you always have to batch the individual language model queries.
So I cache the queries. So if a query has been asked before, I can just look it up,
But apart from that, also you want to send kind of like 10,000 at once to the server?
That we
process
didn't.
that result and get it back?
I mean, that we didn't do. I mean, compared to the scale like of infrastructure, machines in terms of machines and computation in schools, it's not comparable to something here. So we don't do
but
like.
Just like theoretically, I'm wondering, given that, if you have to do that, do you think like the having the right, the perfect invested extraction algorithm still is like relevant compared to that, or do you think it becomes less relevant, or do you think it becomes? Do you think it can be kind of like applied to that scenario too?
Yeah, I think that applies, but I'm not sure if the speed up will be smaller or bigger. Probably smaller, because you have batches anyway. So, but definitely they can apply. Just I'm not sure the performance gain. And I really think that the larger the space is, the better speed up there is. Yeah.
All right, let's thank the speaker.
Thank you.
Thank you.